Hi, welcome to my channel. In this video, you are going to see example for vector space. In my previous video, I have explained about vector space. Before that, I also explained about what is the internal composition and external composition, and based on that, we define the vector space. And following that, we need to prove now that given a set, when it could be a vector space. So I have taken an example for a vector space as, let us take the set V, which is equal to R2. That means it's a set of all ordered pairs which has two components, x and y, where xy belongs to R. That is set of all real numbers. You know that set of all real numbers are going to be scalars, and the ordered pair xy will become vectors. That means whatever the element present in this set will be an ordered pair with two components. That is what meant by R2. If it is R3, we'll get XYZ. That means set of all three components will be there. Now we are going to prove that R2 is a vector space. Keeping in mind the definition of the vector space, first we need to prove that V plus is an abelian group. So V plus is an abelian group means for a group we need to prove that it satisfies the closure property, and it is also has an identity element, it has an inverse element, and then again it has to satisfy the commutative property. Then we say that the given set is going to be a group. Now the given set is, we know that it's R2 set of all ordered pairs. So I have taken two element xy and another element ab from V, and then we are going to show that it is will satisfy the closure property by adding these two elements, because the binary operation is plus here, so we are just adding, and adding to ordered pair should be in this way: right hand side with the right hand side we need to add, left hand side with left hand side we need to add. So we'll be having x plus a, y plus b, and again you are getting two components, so again it is an ordered pair, so hence it is belongs to V, hence it is closed. And then we need to find out what is that associative property. Actually you need not find out, because it is addition is always associative. So we are going to find out next property, which is going to be the identity element. So identity element here, it's an pair, ordered pair, so that is going to be 0 0, because when you add 0 plus x you will get x, and 0 plus y you will get the same element xy, and then we know that that belongs to V. So the identity element here is going to be an ordered pair 0 0. And then next we need to find out the inverse element for each element xy. So obviously since 0 0 is an identity element, minus x minus y is, so it's going to be an inverse of xy, and we also know that minus x minus y all are real numbers, so all that belongs to R. And then the last property, we need to find out that it satisfies the commutative property, that is a plus b must be equal to b plus a. So here your a is going to be in terms of an ordered pair ab, and your b is going to be in ordered pair xy. So when you add, you will be getting a plus x and b plus y, and since addition is always commutative, so a plus x and x plus y are same, and similarly y plus b and b plus y are same. So that means that a comma b plus x comma y is also equal to x plus ay, and that means this is equal to this. I can write it as x comma y plus a comma b, so which is also belongs to V. So it satisfies the commutative properties also. So it satisfies closure property, and it has an identity element which is in the form of ordered pair 0 0, and it has an inverse in terms of minus x and minus y. It's again an ordered pair, and it satisfies the commutative property, hence V plus is an abelian group under the binary operation plus. So the second axiom is going to be V of s is closed under dot. So we know that dot is a scalar, so we need to multiply with a scalar, which is going to be with a, which belongs to f, and the ordered pair x comma y belongs to V. So we multiply a into xy, so the multiplication goes as such ax and ay, and since due to the external composition, so it is going to be V of s is closed under dot, because again you are getting an ordered pair here. And the third one is going to be, we need to prove the 5 axioms below the third property. So that is, if I take one element alpha x1 y1, the ordered pair, and beta is another element which is equal to x2 comma y2, and ab belongs to f. That means I just express the first ordered pair as alpha and the second ordered pair as beta. and a comma b I have taken from f, which is going to be a scalar. Now the first one I have to prove that a dot alpha belongs to v. So a dot alpha is x1 y1. So when the multiplication goes as such, ax1 ay1. Obviously you are getting an ordered pair which are all a real number. That's very important, that whatever we choose should be a real numbers and it must be an ordered pair, and hence only it can belong to v. And then the second one is I need to prove that a into alpha plus beta is going to be a alpha plus a beta. That's what I need to prove now. So let me take the left hand side, a into alpha plus beta. So a into your alpha is this and beta is there. And when you add alpha plus beta, you will be getting x1 plus x2, comma y1 plus y2. And that should be multiplied with the scalar a. Further, I can write this as ax1 plus ax2, comma ay1 plus ay2. So that means this again, ax1 I can split it again as ax1 comma ay1 plus ax2 comma ay2. Now you just add and check. You will be, how do you add two ordered pairs? ax1 plus ax2 and ay1 plus ay2. You are getting this here, isn't it? So I am just simplifying this in terms of this ax1 ay1 plus ax2 ay2. And again this can be written as taking out the scalars, a common scalar. So I can take it out. So that's a I have taken it out, and x1 y1. Here also a I have taken it out, x2 y2. So x1 y1 is nothing but alpha and x2 y2 is nothing but beta. So I have proved that a into alpha plus beta, we can write that it is equal to a alpha plus a beta. And next is going to be, the next property is a plus b into alpha. So a plus b is a scalar. We know that a, b belongs to f. All are scalars, and that should be multiplied with x1, y1. What I need to prove that it is distributive. A alpha plus b alpha I need to prove. So this a plus b into x1, y1, again this is a scalar. So this can be written as common for both x1 and y1. And hence I can write this scalar as a plus b x1, a plus b y1. And a plus b in x1 I can split it as ax1 plus bx1, and a plus b into y1 I can write it as ay1 plus by1. Again this is, this is an addition. So this I can split as such ax1 comma ay1 plus bx1 comma b1. Now just add and see. How do you add two added pairs? ax1 plus bx1, you are getting this, and ay1 plus by1, you are getting this. Okay, so we can write that a plus b into alpha is equal to a into, this is, I am taking out the common scalar outside, a into x1 y1, and here b is common, so we are taking it out. If it is common only, we can take it out. If it is different, we cannot. And a into x1 y1 plus b into x1 y1, though that can be written as a alpha plus and b alpha. So a plus b into alpha is equal to a alpha plus b alpha. Now the fourth property under this axiom is AB into alpha must be equal to A into B alpha. That is associative. So AB into alpha. So same as such, AB x1, AB y1. And this I can take out A outside. I'll be getting B x1, B y1. Then again from this I can take it out B. So B into x1, y1. So this entire thing I can write it as B alpha. So A into B alpha. So AB into alpha is equal to A into B alpha. The last one is an unit element. So 1 into alpha must be equal to alpha. So 1 into alpha. Alpha is x1, y1. So 1 into x1, 1 into y1. That is nothing but x1, y1. So that is alpha belongs to V. So it satisfies all the conditions for the vector space, and hence V of f is a vector space. So it is very easy. Only thing, little concentration is required, and we need to know what are the operation given, what is the set is given. Based on that we can prove any set, whether it going to be a vector space or not. We can easily find out by using the definition of vector space. See you in the next video with some more examples. Please like and subscribe.